Niobium is a uniquely versatile element that has become indispensable as a microalloying element in many high-strength, low-alloy steels, for example in line pipe and structural applications. It is also an essential addition in a variety of stainless steels. Very modest additions of niobium can impart strength and toughness to steels and also improve weldability. Niobium is primarily extracted from a complex oxide ore, the largest global deposit of which is mined and processed by CBMM in Araxá, Brazil. Following a series of enrichment processes, the niobium is combined with iron to produce ferroniobium. This ferroalloy contains around 63% by weight of niobium metal. Ferroniobium is produced in various forms, including lumps, fines, cans, and cord wires. The product supplied for use by the world's steel industry is most commonly in the form of lumps. The consistency of the chemical composition of the ferroniobium is extremely important, and the lumps are carefully graded in size to meet the needs of individual clients. The importance of this will soon become clear. Following primary steelmaking, molten steel is usually tapped into ladles, which are in effect very sophisticated and robust containers capable of holding up to 300 tons of liquid steel. It is in these ladles that various key alloying additions are made, and the overall process is referred to as secondary steelmaking. The ladles must therefore be capable of containing the liquid steel at a temperature between 1600 and 1650 degrees centigrade during several lengthy procedures, which may include deoxidation, degassing, stirring, decarburization, desulfurization, and the addition of ferroalloys. A pre-calculated addition of ferroniobium is made to the ladle to achieve the final chemical composition required. For most ferritic steels, the aim is to produce a product with the typical niobium content in the range 0.01 to 0.1%, whilst for some stainless steels up to 1% niobium can be appropriate. The Ellingham diagram is widely consulted to determine the optimum sequence of additions of the various ferroalloys, and aluminium as a powerful deoxidizer. Ferroniobium is only added when the strongest deoxidizers, like aluminium and silicon, have done their work, but it can often be just after, or in conjunction with ferromanganese. During the time the liquid steel spends in the ladle, a thick slag of iron and oxide-rich material forms at the top of the melt. A hole must be formed in the slag to allow the introduction of the various additions, including the ferroniobium. Depending on the steelmaking process, to enhance the yield of niobium, the ferroniobium can be added during tapping in the early stages of ladle filling from the primary steelmaking vessel, or at a later stage when the ladle is full and further deoxidation has occurred. It is critical to ensure that the state of deoxidation and the temperature of the ladle are correct. During delivery into the ladle, the size of the particles or lumps is of key importance. Too small or fine, and there is a danger of unwelcome losses via the extraction system, or they become entrapped in the slag. If the lumps are too large, they will sink too deeply into the ladle and their subsequent dissolution may be adversely affected. The velocity of the particles being delivered through the chute is also therefore very important. The ladle is usually constantly stirred during secondary steelmaking, as this facilitates the dissolution of the ferroalloys being added. But if the stirring is excessive, creating turbulence, smaller lumps move up and come into contact with the slag, and their alloy contribution can be lost through oxidation. Efficient recovery of niobium is closely associated with the melting and dissolution characteristics of the particles, and dissolution time will be affected by factors such as particle size, and even more so by temperature. Initially, as particles hit the molten steel, which is usually between 1600 and 1650 degrees centigrade, they actually chill and freeze the steel around them, forming a solid shell. This shell gradually thickens until the temperature equals that of the steel's liquidus temperature, at which point the shell begins to remelt. However, in the meantime, the core of the ferroniobium particles will have reached a temperature above 1500 degrees centigrade, and it interacts with the steel from the shell and starts to melt. The shell and core continue to melt, and the process is accelerated by vigorous stirring and careful control of temperature. The process repeats itself as the unreacted core material is uncovered. This video has been produced by CBMM to augment a document that was produced to provide guidance and client support. It includes a checklist of key actions which facilitate the effective addition and recovery of niobium during secondary steelmaking. CBMM aims to ensure that customers can achieve niobium recoveries from ferroniobium additions in excess of 95%. Their support package includes teams of knowledgeable experts with appropriate practical experience, always ready to discuss issues directly with customers. As the world's leading supplier of niobium products and technology, their ability to tailor ferroniobium products directly to meet the needs of customers and technical support package makes them the supplier of choice for many of the world's leading steel companies.